Hi and welcome again to Java Programming 1. This is our first class. So why don't we start talking about how we're going to do the class and how we're going to be managing this. One of the things that I never liked through my academic years or my years as a student is that you would take a class and you would have a required book. And that book, after that entire class, was going to be effectively a paperweight. So in this class, I don't have an actual mandatory book. The reason is because the technology will change also. So as technology will change, I don't want it to be obsolete. However, I do have a recommended book to go along with it, which is Java Beginner's Guide. It's basically the official Java guide. And so that's one of the things that we're going to be basing Java from. Well, at least this class. The next one is a book called Clean Code by Uncle Bob or Robert C. Martin. It's a book that tells you how to write good code. And it's not really necessary for this class, but I do want, if you are really pursuing the class or the career path of being a programmer, I really recommend that you take this book and follow it along. It's a great read. And the last book is Design Patterns. So in the intro video, I was talking about how programming, it is like cooking. So Design Patterns is basically a cookbook of problems that have already been around and have already been solved over and over and over again. And it is written by the very famous Gang of Four, as they nicknamed themselves. It's a really old book, but the design patterns remain the same, which goes back to my thing about me trying to focus more on the theory rather than on the technology per se, because the theory will change dramatically less with time. So how are we going to structure the classes? The classes, we're going to be doing some assignments in teams. We're going to be having lots of hands-on exercises. We're going to be doing code reviews, and you guys will code review each other. There's one quiz that is not really a quiz, but most like a mini final project, and then there's a final project. Let's dive into our first class. What I want to explain a little bit is different categorizations of computer languages, and the last two are more like an internal programmer joke. But the main thing about the different types of programming languages is that there are interpreted versus precompiled versus native. And let me explain something with that. A precompiled language versus interpreted. Let me just use this as a whiteboard where we have precompiled. A native language, and even let's start with a native language. The computer, and you probably heard this cliche that the computer only knows zeros and ones, right? Zeros and ones. That's what the computer understands. So then, how do you translate from zeros and ones to numbers, dates? Even video games, etc. How does a computer understand zeros and ones? Let's see. Okay, so if we are in this world of native, what the computer understands, then a native language is essentially going to talk to the computer in terms of this native language or close to. And this brings me to a different topic where we have low-level and high-level languages and low-level. So we have high-level and low-level languages. And a low-level language would be something that is closer to the computer, writing in zeros and ones. A high-level language is something that a human can understand. So first of all, I've got news for all of you that might not have much programming experience. First of all, is that you already know how to program, and the reason why I'm saying that is because you already are programming every day of your life. You are somehow writing algorithms where it's because you're solving problems. That's an everyday thing. Like you are driving towards the store, and you see the traffic light, and if you see the traffic light, you stop, and when it's green, you continue. And so I can give you a lot of different programming exercises, or at least programming problems, and you would be perfectly capable of solving it. In the same way that there's low level and high level languages, you are already somehow programming or using a programming language when you do this. Hey Siri, what's today's date?
It's Tuesday, April 7th, 2020.
Basically, Siri is a high-level programming language. And if I was going to ask that question, I would probably write it in a lower-level programming language. Any other languages, Java could be somewhere in here. C could be somewhere in here. C++ could be here. Python is a little bit here. JavaScript is somewhere in here. And so on. So, by the way, do you guys know why it's called C++ and C#? In Java, the way that you increment a variable or add one to a variable is by using the plus. In Java and C as well, because C was the same way. C was not object-oriented, and C++ was object-oriented. So the idea of why it was called C++ is because it's C plus 1. That is why it's called C++. Now, the idea of C# is in a piano. This is a clever way of naming the same language something else. So if you have a piano, and this is the scale of a piano. Yes. If you have the scale of a piano, and this is the C note, this is the C# note. So it is the C note plus 1. It's the same concept, just explained differently. And sometimes programmers like to do that kind of silly jokes, like, oh, it's C++. Why? Because it's C plus, it's a little bit better than C. Oh, okay. Ha ha ha. So anyway, when you have that hierarchy of languages that go from low level to high level, and low level is, computer speaking, then you have a different panorama. So that is a native language. Anything that is close to what the computer does. Now, the question then could be, how does the computer interpret all these things? Well, first of all, it's all different type of encoding and descriptions that the computer might do. So, for example, a photograph is not going to be, a photograph of, say, a dog. It's going to be like, oh, the dog has, brown coat. It has a lot of furry stuff. It has, it's not going to be that. It's going to be more about the pixels, a description of the pixels and how they are encoded and compressed. So if you have a photograph, it's going to say, okay, pixel 0, this one, this is the RGB or red, green, and blue values for that pixel. So color it this way. Pixel 2 is going to be also its RGB values. And then 3 are RGB, etc., until it finishes. So that's how encoding of data works. But the computer really doesn't know how to understand that. So when you're talking in the computer language to the computer, you're basically saying, load this data, load it into memory, pull it in from the hard drive, put it in here, do that. So it's more about the descriptive operations that happen. When when you're talking about interpreted and precompiled, the interpreted, we're actually going to leave it at the very end. But precompiled is a much more refined mechanism of interpreting the language. So there is this thing that says, I don't know if you guys have ever seen like this internet meme that says that it has two bears. And let me just remove this line. And it has two bears. And I'm just doing quick drawings of two bears talking to each other, saying, "Let's eat, Mom." And there's another third bear here, which is the mom. So under this unrefined language, you can make the mistake that the bears are going to eat their mother. But if you have a more refined language that adds a comma, it's that the kids are telling the mom, "Hey, let's go eat." So you can see how a better grammar makes things more efficient. You don't have to ask questions again or go slower because you have to really think about things. So if we write "let's eat, comma, Mom," you understand that you're telling your mom, "Let's go eat." But if it didn't have the comma, if it did not have that comma, it would be "let's eat, Mom." So you're like, wait. Do you mean "let's eat, comma, Mom," or "let's eat, Mom"? That can lead to some confusion. So the analogy that I'm trying to make here is that a precompiled language will grab whatever code that you did and run it through an optimization phase and verify that all the syntax is correct. So before you even run the program or before you even get to build the tool, you will know if it will compile. So that's one thing. So let's write it down here. Precompile, you will in advance know if it will compile and if there's potential problems. Second, it will optimize the code for faster execution. Interpreted languages is similar to me trying to communicate with somebody, say, from Russia, right? Where I don't understand the language. I don't even understand the characters that are in Russian. Let's put here a Russian flag and here, I don't know, an American flag, or any other language that uses a different than Western language, or even if it's not Western, like say that it was Germany or something that has a very different language, grammar structure, and things like that, where you really cannot communicate or will be able to communicate. In the case of an interpreted language, it's a live translation between the two characters that are being, let's put it this way, encoding and decoding the messages in real time. So it's, in that sense, it's less efficient. And not as optimized. Why is it not as optimized? Well, because it doesn't have enough time to re-optimize the code and then run it and be fast enough for the user. Examples of precompiled languages are Java, C, C++, C#, anything that you utilize a compiler. Examples of interpreted languages, it's JavaScript. We have Python, etc. So there's different types of languages. In this case, you do not need to precompile the language before you actually send it and distribute it somewhere. Any questions? So in a precompiled language, you get the original code. Java. I wrote Java. And then you run it through the compiler, which here is going to check the syntax. Oh, it's thinking that I'm writing circles. It's also going to do native translation and optimize the code. So what do I mean by optimizing the code? The code optimization is more like when you have a very complex algorithm and you have certain parts of the code that the compiler is going to analyze and say, this part will never run, or this part needs, it can be optimized from, let's say, just visually, if I can explain something a little bit better, and let's see. Let's assume that for optimization, let's assume that the black boxes is the code that it's going to execute, and what it's going to end up doing is as an optimization is that it's going to put all those blocks together where there's no more white spaces. I don't know if that is like an analogy that could work in this case, but the idea is that for example, if you're using something that it's allocating too much memory, like if say you're making something that has the number 1 and you're saying, oh, I need 1,000 bytes for this, the compiler is going to be like, but you never really changed that value, so I'm actually going to re-optimize it and make it a 1-bit data type, because the compiler already knows and looked forward to see what was the actual value. So the compiler can do certain optimizations like that. An interpreted language, and it has actually, this technology has improved a lot in the recent years, but especially with JavaScript. But in the precompiled language, the compiler actually spits out a different file, and this is a file that you distribute. You distribute this file to other computers. So in the Java exercise, it's a .class file. That's the file that you send. Also, you know what? It removes a bunch of unused functions, and so if this say was 10 megabytes, after optimization, the .class file is going to be 100K. You know, like it does like even size optimizations and things like that. So compression of files. It's among the many things. The difference between an interpreted language, which is now the second part, is that the difference between the second part is that you have your source file and then you put it directly into runtime, and that runtime translates it directly into zeros and ones. In this case, the class is the thing that is executed, and that is the thing that is now putting zeros and ones. So we added in the precompiled, there's an extra step. Here, we went directly into the runtime, or the area where the code is going to be executed. So for example, JavaScript follows this pattern, because if I go into, say, let me go into UCLA extension and I load this, you can see that directly I am downloading the source of a bunch of different JavaScript. So you can actually read this, right? So that is the source code that gets interpreted. Let me just move it to the side so that way the runtime is the browser, and that essentially displays or does whatever modification that we need to have. That's the biggest difference. But because it has to like really get the source code and get it into the runtime and get it into code in a very fast way, what it does is that it does a live compiling. And because it's live and it's not taking as much time, it's as good as fast food. You know, it's in some cases it's sufficient. You know, like if you get like I don't know, Panera bread, that it's not as bad for you. It's it's gonna be okay. It's gonna have a decent runtime, and it's but is it gonna be as good as an in-home cooked meal? Not really. So that said, the runtime / compiler will take a lot of shortcuts to get it as soon as possible into the execution of the program. Let me put it this way: I'm not really against any programming language the same way that I'm not really against fast food. Sometimes you're on the go and you're in a hurry, and you need to eat something because you're starving. Like there's nothing wrong with really stopping at McDonald's, other than if you make it a habit. But in some cases, at the end of the day, a programming language is a tool. And a good friend of mine used to say, you got to use the right tool for the right situation. So if the right situation that you're trying to solve for is, you can do a quick and dirty code, then an interpreted language is just perfect, because it allows you to very quickly iterate over the code. Whereas a compiled language might take longer, because you are compiling, then executing, then compiling, then executing. It has one extra step. So again, it all goes back to determining what you want to do with it. Okay, so then let's go into the next point, which is statically typed versus dynamically typed. A statically typed language is what does the word static mean to you guys? Just let's talk about it, because it's an important concept, like, of what it means to be static. Okay, so basically, not changing. Let me then also, because everybody really understands that static means not changing or not dynamic or not moving. Number one thing about Java, whoever wrote it was horrible at setting natural names. And we'll talk about later what the keyword static means, because every reasonable human on Earth understands static from not moving, but whoever wrote Java decided to use the word static for a different concept. So we'll talk about that more later. Anyway, so we have static versus dynamic language. Okay, what does statically type? If you have a statically typed language, that means that once you define a variable, for example, in Java, this is the way that we define a variable. You say int x equals 1, and essentially this is saying that this is a number. Once you create that variable, I cannot say x equals c, because the compiler will say, wait a minute, this value does not relate to what an int is. Because it is statically typed, in this case, it's correct to say it doesn't change. In the case of a dynamic language, like for example JavaScript or Python, in the case of Python, you can say x equals 1. And then later you can say x equals c. And both of these are valid things, because you can change whatever value that it's holding to be dynamically typed as the code goes in. Or even in JavaScript, which is var x equals 1, and then you can do var reassign that x into C. So that's, for example, a JavaScript, and this is Python. So Java falls in this category. C++ loads in this category. So that's the statically versus dynamically typed. Once defined, you cannot change it. And on the other one, once defined, you can always change it. Item on the list. Strongly typed versus weakly typed is the similar. Spaces, brackets and spaces is just as a joke of how languages like Python or Ruby work with indentation, and Java works with brackets. And spaces versus tabs is just a very nerdy thing, so let's just ignore those. It was, when I wrote it, I thought that I could put some computer humor, but it's, now that I look back at it, it's a little silly. Okay, let's talk about what is so great about Java. And I'm going to give you the pros and cons about Java. I'm going to give you, the advantages versus the disadvantages of Java. And I'm going to try to keep it as real as possible so that way you're not oversold in Java or undersold in Java or oversold in any other language. When somebody says, oh, this language is better, I don't really believe in that. I only believe in you're using the right tool for the right job. So, what is so great about Java? And in this point, I like to then go back into my whiteboard and explain a little bit of computer history, because understanding that we know that the computer speaks zeros and ones, right? A combination of zeros and ones mean things. And why does a computer only speak zeros and ones? It's very simple. The zeros and ones part come in from the fact that you have light switches, basically. So either you turn on the light or turn off the light. And internally, a processor has a bunch of different billions of light switches that mean different things. So if on byte 30 you turn it on and then everything is zeros, that means one thing. Or if you have something like that, means another thing. So you can have processors that understand things coming in this direction, but you can have processors that understand things coming in this direction. So in the early days of computers, even before Intel became big, there were very diverse CPU manufacturers, including Apple, that had the PowerPC processor. You had or processors that, if you want to go into more computer stuff, the RISC architecture or the CISC architecture, that is irrelevant right now for the class, but in case, I'm just giving you the names so that way in case that you want to Google them. But you could have like Intel, AMD, different architectures that would interpret some of the data differently. So when you had a computer that was running Windows, let's see if I can do the Windows logo, and a computer that is running Mac, let me see if I can try to draw a better apple. Well, that's an apple. So you had a Mac, and then you had an HP server, like HP UX or a Solaris box. All these computers were and are running different languages and running different operating systems and even running different processors. So essentially, something that let's just for simplicity, that if this meant hello, and this is not exactly what it means, but if this code meant hello, in another processor it would mean goodbye. So obviously, if it's an opposite or an unintended result, then the same program cannot be run from one computer in another, and then in another, and then in another. So that's then where you have problems of executing the same code in different machines. And even because of that, that meant that once you wrote a program for Windows, you could not run it on a Mac. And you cannot run it on any other machine. So, fun fact, that's how Microsoft became so big, because Microsoft focused on building the development environment and made essentially a lot more content for the machines, including the popular items like Excel or things like that. So basically, this is just content for your computer, the software. And if you cannot run the same software on other machines, that was blocking you from different platforms. So sounds great for Microsoft that you are not able to run the same code in different machines, but it's not great for the user. And also it's not great if, say, you decided to write something in this architecture, but you have very expensive servers here. These two are very expensive servers. and you cannot just translate the code from here to here. So that becomes a huge overhead cost for anybody that is developing software, which then the idea was, what if you could run the same code everywhere? What if you only wrote it once? Where is it? If you only wrote it once and ran it everywhere. So that's one of the main advantages of Java. How do they do it? Well, we're going to talk about it in a little bit. The next one is that it's secure. And what I mean by secure is that old school programming, now it's done more like this, even built into the OS, so you really cannot hijack a machine. But back then, you have your CPU, and then you have your memory, and even you have your hard drive and whatnot. The way that it works is that if you start a program, the computer is going to try to load whatever into memory and then send it to the CPU as needed. So this is the RAM, and this is the hard drive. So the hard drive is going to load a file, it's going to load it into memory, and then the computer is going to go back and forth between the RAM and the CPU to read and execute whatever values on that program. Which, because you have a single shared RAM, if you have a second program that is running on your computer, and you know that computers just let me actually load this so that way you can see that computers have multiple programs running all at once. Where did it go? Oh, here it is. So you can see that there's a bunch of different programs running all at once in my machine, a lot of them. And they're switching on and off, on and off, on and off. And as one program is running, it could go in, and let's assume that the things in color red is the data utilized by program 1, and the ones in yellow here, can you guys see the different colors? Let me go into like a blue, actually. The ones in blue here are parts of program 2. So again, we have blue and red, and it is program 1 and program 2. You could have easily, because program 2, as it's reading from memory, you could have program 2 easily go in and into other cells of the computer and hijack that memory. And all of a sudden, you have this corrupt memory right here that could be a potential problem. So Java, what it does is that it isolates memory processes. So that way it can control the objects that are created by itself, and B, protect the memory from being hijacked by other processes. And Java was the precursor of that. Java was the first one to do that thing. All right, so in the next point is that it's object oriented, and for this, you guys in around class 5 or 6, you're going to understand more what is object oriented programming. But basically, object oriented programming is a way to describe the world for the computer in terms of objects rather than zeros and ones. So it helps the programmer build a world that it's or describe things that are more as abstract concepts, like 10 computers in a classroom, things like that, things that are abstract, filling those things in. Okay, all right. The next thing is that it's robust. And what does that mean, robust? Or at least the guys from Java sell it because we're using strongly or statically typed. is a robust language. That means that if you are defining an integer, like we saw earlier, okay, so if you have an int x equals hello, the compiler would be like, this is not robust because you are saying that this is a number, but you are defining a string or a word. Let's put it like that. Word would be simpler. So that's one of the things that Java programmers, or at least the Java writers, clear ink, what is that? Yeah. The Java programmers list as an advantage the fact that you can ensure that once something is defined, it stays that way. The next one is good exception management. So things happen in code. Sometimes you are downloading files from between two computers, and you are, transferring a file, and all of a sudden that connection drops out. In a Java programming language, you can handle something when a problem is going to happen and recover from it. So that's what it's known as exception management. So Java has good exception management, and for those two reasons, it's considered a robust language. The next concept, multi-threaded and distributed environments, are concepts that Java was a pioneer in the 90s to do, because Java essentially was going to be known as the language of the internet. And initially, when Java was released, the idea is that you could run a plugin that would have a full program in your browser, and that would be an applet. And that was like the idea really never took off because it was a program within a program, so it was a little heavy. But the idea is that it would be the language of the internet. And within the same lines, the internet, as you guys know, and there is not just a single computer, for example, in the case of Google, right? Where it's only one single computer processing the data. In the case of somebody like Google, a request comes in, and then it goes into an army of machines that will process the data, and then will return it to a master machine and then return it. That's the way that basically Google works. But the fact that it's using all these different machines to respond to a request, that is a distributed programming thing. The other one, it's essentially the same thing, but within your own computer. So if we are looking at this thing, you're going to see like threads, and we're going to try to find, what is this? Categories or MD5. Let's see, sharing D or the notifications center, or even my Java updater is using 6 threads. That means that a single process split its job into multiple workers, and then it's going to perform something heavy and then continue as a single. Say you have a process, and you are splitting that process into many other sub-processes, and then those processes might come back later to a single process. So essentially, multi-threading is the same as having multiple people working in the same problem, but that is all within your computer. You have the same multiple processes running on the same computer. So if, say, you have to sort 100,000 numbers, you can divide this by those 100,000 numbers by, say, groups of 5, and then you'll get 100,000 divided by 5. You're gonna get 20,000. Right now my brain is shut down after a long day of work, but you're gonna get each process is gonna just process 25 as opposed to one single that it's processing 100,000. So it's like a divide and conquer for both situations, distributed and multi-threading. So Java has a built-in multi-thread and distributed environment programming, and we look at a lot of that very thoroughly on Java 2, by the way. Multi-threaded programming is a very difficult thing to do because there's always lots of little details, but we review it and I try to teach it on Java 2. It's fast. Yes, it's super fast. It's one of the fastest languages in the world. Oddly enough, a lot of the techniques for Java then were later implemented by JavaScript. When Google hired the main architect of Java to try to improve the Chrome browser so that everybody could enjoy a better internet. So yeah, it's one of the fastest languages around right now. In some cases, some tests actually, because of the amount of optimizations that Java does, and this is because it's a precompiled language in this case, it is a very fast language. And the last item on the slide, it is that it's very popular. So according to Octoverse, which is, let's see if this statistic still holds. According to Octoverse, which is, Octoverse is more like a summary of the year in GitHub. According to Octoverse, where is this community overview, dependency, overall communities, top languages. You can see it used to be number 2 until 2018 when it dropped down, and Python now is passing it. Languages like C# come and go constantly between C and C++. But Java for many years was the king. Now Python, I think, because of data science and because of Django, it's a very popular yet powerful language. So it's, again, let's just review those points. It is portable because that you write it once, you run it everywhere. It is secure because it performs memory management on itself, and it also does memory isolation. It's object-oriented programming. It is very robust. It is good for multi-thread and distributed environments. It's really fast, and it is really popular.